Hello everyone. Can you hear me? Hello.
Sir, good evening, sir.
Yeah, good evening. How are you?
Fine, sir, fine.
Yeah. Shall we wait for a few more minutes to everybody join? Or
Sure, sir.
yeah. You can see right now presentation.
Yeah, visible, sir.
Yeah. Okay, that's good. So meanwhile, I will introduce myself. Okay. My name is Allu Vinod Kumar. I am from IIT Delhi, Mechanical Engineering. Why don't you introduce yourself one by one? Just your name and what you're studying and yeah, like that. Yeah. Anyone can start. So it would be much more interactive, right? So it is not like a just a talking and like that. So who want to introduce yourself? Just your name and what you're studying now, like BTech or which year, and yeah, like that.
So I am Anandan, working as an assistant professor uh, in Power Engineering College, Department of Mechanical Engineering, sir.
Okay, that's good. Thank you. Next,
Thanks.
next, anyone want to introduce?
Yes, sir. My name is Shailesh, and I am working as a PhD research scholar in NIT Jalandhar.
Okay, that's
And
good.
currently I'm in fourth semester.
Okay, that's good. Okay. Next. Hello, is somebody lefting? Left? Uh, oh, yeah. Yes. Okay,
Hello,
yeah.
my name is Parsappa Mani.
Okay.
I
Yes.
am working as assistant professor in Nutan Engineering College of
Oh,
Pune.
okay, that's good. Good. Uh, Thank you. And next.
Hello everyone, this is Chaiteja.
Oh, yes.
I'm working as assistant professor in one of my Academy Institute of Science and Technology.
Okay, that's good. Okay, I think we can start now. So, you're part of you're registered for the course of nature of and properties of materials, right? So, in going the today now introduction. I mean, today session about how to solve the assignments for this course and so on. So before that, we will just a brief overview of just two slides. What is the different kind of materials and I mean how we classify them. What is the different kind of material properties and so on. Okay, so we can broadly classify materials into five ways, right? One is metals, polymers, elastomers, glasses, and ceramics. So, what is how we can differentiate between metals and non-metals? Can anyone say?
Yes, sir. There should be exactly one metal.
Um,
If
okay, good. Next, continue. So one. Okay, what is the some of the characteristic properties of metals compared to non-metals or ceramics? Okay, you are now considering metals and ceramics. How do you differentiate between both of them in terms of properties? Because our course is mostly about what is the materials and what is the properties and nature, right? So we should most focus on what is the properties of each kind of material, what is types of materials we have, and what is the properties of that kind of materials will possess. Okay, so in metals, what is the some of the characteristics, some of the fundamental properties it has? So and ceramics, some of the fundamental properties it has, and polymers have some of the fundamental properties like that. Can you differentiate between metals and ceramics now? We will discuss about remaining thing later. So first, let's limit ourselves to metals and ceramics. So can you differentiate what is the some of the fundamental properties we can observe in metals in general?
Sir, in metal we have a valence electron. So
Yeah.
basically, these electron moves and they share their electrons to
Yeah, that's
with
good. That's
other
good.
elements.
Yeah,
Yeah.
that's good. That means it has very good electric conductivity. It gives it to exhibit the metals generally tends to have good conductivity compared to ceramics. Okay, what kind of bond we can see in metals and what kind of bonds we can see in ceramics? Any idea? Atomic structure we have now. The ceramics have different kind of bonding, right?
In metals we have ionic bond.
Okay. In
Uh,
ceramics,
in ceramics, I think we have covalent or
yeah. Let me tell. There are three kind of bonds, right? Ionic bond, covalent bond, and metallic bonds. Okay. So in covalent and ionic bonds mostly exhibit in ceramics. Okay, that's why those have no valence electrons. To I mean outermost cells also tightly bound to the core, right? In metallic bonds have only mostly metallic bonds only, metallic kind of way. Okay, that means entire it will be like a grid of pattern of all core nucleus, and electrons are freely flow into that matrix. Okay, that's why it is a good conductivity of thermal and electrical conductivity, right? In ceramics, what we see is that it has atomic or covalent bonds. So there is no free electron to motion. So which results in what kind of property? We can see there is no free electron to motion. So what kind of property we can see? Metals have lot of free electrons, right? Because of metallic bond. So it will be passing the higher current rate and so on. So in ceramics and like that, it is a covalent bond and ionic bond. So there will be no free electrons, right? So which kind of property we can observe? Any idea?
actually it has low thermal conductivity,
Yes, that's good. And low thermal conductivity. In which conductivity also very less?
electrical conductivity as well.
Yes, electrical conductivity also very less. Okay. Coming to strength, what we can say about the strength in metals and ceramics, how we can differentiate between both of them? Yeah, it is just rough idea. It is mostly I want morely interactive way of to talking with you and like that, right? It is just to yeah like that. Yeah. Any guess, any idea, any whatever comes to your mind, to it will be much better because so it will be much more learning for everybody, right? Yeah.
Sir, basically in ceramics, that is brittle in nature.
Yeah, yes, that's good. That's good.
So,
In metallic, which kind of property we can observe?
so in metal are mostly ductile in
Yeah,
nature. Like
yeah. That's good. That's good. Metals, we can see most of the case it is ductile in nature. Ceramics, we can all are exhibit more less more brittle in nature. Okay, that's good. Okay. So how we difference between polymers and elastomers? Okay. What is the polymer? We can say. Any idea? Polymer. And okay, we will see in terms of uh, mm, okay, we don't go to polymers yet. Okay, ceramics and glasses. How we can differentiate between ceramics and glasses? Okay, in both of the cases, we can see the same covalent bond and ionic bonds in both of the cases. But what makes it bothly different? And ceramics also brittle, glasses also we can see like brittle failure, right? So how it is different from one to other, ceramics to glasses? Yeah.
So I think actually, in my perspective, glasses are amorphous in nature, right?
Yeah, yeah, that's good. That's good. That's absolutely correct. Glasses are amorphous in nature. Ceramics are, if amorphous
Ceramics,
opposite what?
that is crystalline. Yeah,
Yeah,
crystalline.
crystalline. Yeah, ceramics are mostly all are crystalline in nature. Glasses are all are amorphous in nature. Amorphous means it is random in crystal structure. There is no fixed orientation. But ceramic has much more order structure. So it has much more higher strength but brittle in nature. Okay, because covalent bond, iodic bonds are very strong bonds. So those generally results in higher strength, but it is less ductile. Okay, coming to elastomers. Elastomers. How we can differentiate to elastomers? What is the mean of what is the some of the fundamental characteristics we can observe in elastomers? Yes, please. Yeah. Elastomers. Okay, we will break it down. There is just some clue in the name itself. Okay, in rubber, what kind of property we can generally see in rubber, rubbers, and that kind of what kind of property we will see in rubber compared to metals and other things. It is a half of the name. It has hmm?
Elasticity, sir.
Elasticity. Yes. In polymers, okay, okay, we will go to polymers later. Elasticity means, okay, in metals, if we expand it in a elastic region is around 1%, 2% like that only. But in elastomers, it is more than 10%, 50%, some goes 20% like that. If we stretch a rubber band or something like that, it will expand much. It is actually when what we can call rubber as a brittle material or ductile material in a what we can call, if we have a rubber band or a tire rubber, anything we have, right, generally we using one, what we can say whether it is a brittle material or
Is ductile material. Ductile material, sir.
ductile material. No, it is actually brittle material because it elongation, entire elongation is happening in elastic region, not in the plastic region. Okay, when we leave the, once we stretch it, it will elongated very long. Once we leave it, it will come back to its original position, right? It is not deforming, right? That means there is no plastic deformation is there. Okay, you are understand, you got it right. So wait, I think yeah. So but what is the mean of plastic deformation? Means plastic deformation means it's once it is deformed, it will be stay in the deformation position. But in case of elastic materials, it will expand and it will come back to its original position because of it has the elastic range more than 10 percentage, 20 percentage. So it will expand and it will regains its original position. Okay, uh, so we can't call it as a ductile material. Ductile material means it should show the some plastic deformation. Plastic deformation different from the elastic deformation. You are getting, or you are getting bit confusion about it. I will explain again if you not getting it. You are getting right. whatever I'm trying to say. Yes, please. Okay. Uh, I think if it is okay. So here is the in rubber band. If we stretch it more, it is elongating only in the elastic region, not in the plastic region, right? So we can call it as a. But once it crosses the elastic region, it will immediately break. Okay, that means plastic region is very small, so that's why we call it as a brittle material, not a ductile material. Ductile material, when we call some material as ductile, is when it is deformed in the plastic region. Okay, plastic region means it will expand and it will stay in that position, not in a deformed position. So that's where polymers come. If we take a polymer bottle or something, if we stretch it like that, okay, it will ductile more, not elastically elongated. So once we stretch it, it will stay in that position even though we have to leave the uh, applying force. Okay, you are getting the difference between polymers and elastomers, right? You are getting right. What is the difference between polymers and elastomers? Hi. Or if not, I will explain that part again. Any query regards that?
Sir, rubber is an elastomers, right?
Yeah, elastomer. Rubber is an elastomer, so it has a elastic. Okay, I will draw, so it would be much more better to explain. So, yeah. So here is the typical stress strain diagram, right? So here is, if you consider a steel up to here, we can call it as a elastic deformation. Okay, if consider this one is a stress and this one is a strain, don't take graph is too much because I am drawing with mouse, so it will be a bit difficult. Okay, so this is the elastic region. It is generally around 1 or 2% in case of metals and other materials, right? Ceramics, it is much lesser, around 0.1 percentage, 0.2 percentage, like that. In glasses also same case. Okay, but in case of elastomers, it is around 10 to 20, 30 percentage, like that. Okay, this elastic region. Okay, why we call rubber as a brittle material? Because it is elongating in a this elastic region, not in the plastic region. Okay, if I stretch a rubber band and if I leave it, it will regain its original position. It will not change any deformation. Okay, if I stretch it to its breaking point, once it crosses this elastic region, it will immediately fail. So if something failing after this elastic region, we call it as a brittle material, right? Okay, so that's why we call it as a rubber as a brittle material. In case of plastic, suppose if I take a plastic bottle or something, if I stretch it, once it crosses this elastic region, it will stretch more up to here, then it will break. If I remove the load from here, it will deform and it will stay in that position only, right? Once you have stretched it, it will dimensions will increase and it will stay on that position now. So that's why we call it as a ductile material. That is the difference here. That's why rubber called as a brittle material. It has a elastic region is much higher, so that's why we are seeing as a much more elongation. Okay, you are getting right now. You got.
Yes, sir.
Yes. Okay. Yeah. Okay. Okay. So yeah, there are five different kind of materials, right? Hybrid materials means in some cases we can take some elements of metal, some element of ceramics, make composite material, and sandwich material, and taking of combination of these two kind of materials or these two kind of materials, like that we called as a hybrid material. So these are the fundamentally broader classification of the materials, right? So yeah. So coming to properties of the materials. Okay, what kind of properties we can observe in a material in general way? So coming to first one, chemical properties, right? So what kind of chemical properties we can see? Composition. What kind of composition it has? What kind of atomic elements constitutes it as, right? Some case it has which kind of elements it has? Suppose it has iron, it has nickel, or how much percentage of iron, nickel it has, or it has carbon. It has what is the kind of has composition? You know, right? Composition. Coming to microstructure, you know microstructure, right? What is the kind of grains it is forming microstructurally, how it is the forming, right? Some kind of coarser grains are there, finer grains are there, like that. Okay, coming to crystal structure, what kind of crystal structure we can see, like a BCC structure, FCC, HCP, and simple cubic or amorphous structure, like that. Okay, corrosion resistance. Iron is a pure corrosion resistance, and copper is a good corrosion resistance, like that. Okay. Coming to dimensional properties, we can see. I mean, in terms of physical property for appearance, how it is appearing. Okay, roughness means we are all generally familiar with roughness, right? Smoother surface, what we can call it as a smooth, and what we can call it as a rough surface, right? Roughness means what is the wait, I will draw. So suppose if it is surface, and in microstructural level, if it is a more irregularities on the surface, we can call it as a more rough surface. If it is a less irregularities, we can call it as a relatively smooth surface. Okay. And waviness, what is waviness? It is irregularities but a bit longer bit longer way, like this way. Okay. Difference between the roughness and waviness is that roughness can be like this way. Okay, waviness is the bit to scale is bit longer. You are getting right difference between the waviness and roughness. Lay is also similar one, but it is covers much more. uh, okay, I will draw it. If we do the machining operation, I think most of the people from mechanical engineering, right? So you are familiar with some machining and slot machining, other machining, right? So if generally if I do some machining operation, we can see the patterns like a straight line kind of things, right? Along the cutting tool. So this is called a lay. Okay, and kind of surface finish, outer flat, and so on. Okay, these are the dimensional properties. Mostly how it is appearing to outside. Mostly the surface properties, how it is appearing. So on. Okay. Uh, Coming to physical properties. What we can say about physical properties? One is melting point. Melting point of the material is also important, right? So iron has around 1500 degrees, tungsten around 2000, something like that, and every material has its own melting point. If we combine two three materials, its melting points also varies, right? Okay. Second property we can see density. Density is how much amount of per unit volume, how much it is weighing. Okay, how much amount of it is weighing, how much uh, 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 fact return. Okay, next specific gravity. So how we can differentiate between density and specific gravity? Okay, any idea?
For specific gravity, we will be having G, sir.
Okay.
But with the density, we don't have any gravity.
Yeah. Okay, density into specific gravity gives the which property? Density into specific gravity of the material. but it will give weight. How we get the weight? Density into specific gravity only, right? Okay. And next, thermal conductivity, thermal expansion, and electric resistivity, and refractive index. Thermal conductivity or refractive index. What is the refractive index? You know, it is mostly the reflective reflection of the waves, electromagnetic waves, right? So, uh, black body, white body, you know, right? Black body means it absorbs the all incoming rays, right? So, in white body means it is reflects the all falling onto the surface. Suppose if I have a surface, if it is observing all light, we can call it as a black body. There is no emission. Reflection back is zero. All is observing. But in case of uh, in case of white body, there is no absorption at all. All are reflecting back. Reflection is 1. Absorption is 0. Here, reflection is absorption is 1. Reflection is 0. Okay. But in general case, no material has the perfect absorption of 1 and no material has the perfect reflection of 1. Okay. Some cases, some material will absorb some amount of the light around 0. So for example, 0.2 and so on. Suppose it is observing, and uh, it can reflect suppose 0.7. And what about remaining 0.1 percentage? It could be transmit, right? Suppose if this material is up to this much only, so some material 0.1 can be transferred here, right? How much of the material is transferring? Okay, this is the reflective index. Next, to thermal conductivity. How much? How fast it can be thermally conductive? We already see the difference, right? Kind of material also affects the thermal conductivity. Metals are the very good thermal conductors. Ceramics, glasses. Ceramics are poor. Uh, okay, but not that much thermal conductor. Glasses depends on the material composition. It varies. It is not like a every ceramic don't abstract the thermal conductivity. It is different from electrical conductivity, right? Some ceramics have good thermal conductivity also. So next, coming to electric resistivity, nothing but electric conductivity. Okay, what is the specific heat? Any idea? What is the specific heat?
Yes, sir. It is amount of heat required to increase the temperature by unit
Yeah, that's good. That's good. Very good.
unit mass of a gas or what.
Yeah, that means water around 4 point something is there. It is like how much amount is energy we have to input to increase the unit amount of the temperature. That's good. What I is saying, right? And what about the thermal expansion? Thermal expansion. Thermal conductivity we see, right? How if I give 100 degrees of the temperature at one side, how fast it is transferring one end to other end to reach the 100 degrees. Okay, if I have a, okay, I think I will write here. If I have a one body here, if I applying a temperature at here, suppose 100 degrees. Okay, how fast it is time takes to reach this 100 degrees at this corner? That's, we can call it as a thermal conductivity. What about thermal expansion?
Due to change in temperatures,
Yeah, change in temperature.
uh, when an object expand large to change in the temperatures.
Yes, this, that's good. That's good. How with unit degree of temperature change, how much amount of this material is expanding or contracting? That is, we can call it as a thermal expansion. Okay, thermal. Okay, these are all are comes under physical properties of the material. Okay, coming to mechanical properties. Mechanical properties we mostly use it in terms of engineering applications. Okay, chemical properties, we are all aware of this one is microscopic level. Physical properties, we use not for, I mean, in, we must understand this one to get the in mechanical properties. Okay, coming to mechanical properties, because this is mostly used in engineering applications, right? So coming to tensile strength. What is tensile strength? Tensile strength, how we can say something as a define as a tensile strength.
Sir, actually, I have confusion in this
Yeah, sure.
because what I understand is tensile strength is related to the percentage elongation.
Yes, 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 that's good.
So
But yeah, how much amount of the force required to elongate it per unit length? Okay, if I have a iron bar, okay, I will explain you well. Yeah, I mean, bit wait here. I have a here is a one iron bar. Okay, okay. Now I am applying the pressure in tensile mode. Okay, okay, leave it. Consider this one is a perpendicular. Okay, so how much amount of the force it required to elongate this one to suppose 1 centimeter height. Okay, if I took iron, just assume this bar is a iron bar, I have to apply more pressure, more amount of the force in both of the direction to elongate it for 1 centimeter. But suppose if I elongate a aluminum, I don't require that much amount of the force to elongate it for a 1 centimeters, right? You are getting right. What is the tensile? What is the difference? Amount of the force required to change in per unit length in terms of applying force direction. You got it? Any queries?
okay, sir. Okay, sir. But is it dependent on hardness as well? If we
uh,
have more hardness,
no,
so can we
hardness.
say
No, definitely not. Hardness is totally no. Both are independent. uh, Not like a hardness material can be have higher strength, higher tensile strength, or may not have, but it is not a necessary condition. Both two are bit independent properties. We can't correlate between each properties. Somewhat both are mm, I mean both are different only, not we can compare it like that. If some material have higher hardness, it not need not to be higher strength tensile strength. Okay, so like that. It is not a dependent property. It is independent property. Okay. Coming to compressive strength. What is the compressive strength? It is similar to that one, but opposite case. We are applying in the opposite direction. Okay, we are talking about hardness, right? After this compressive strength, I will go back to hardness. So we will get more into difference between both of them. Well, okay. So if I am applying the same force in opposite direction, for changing unit length for 1 centimeters or like that, how much amount of the force required? Okay. Uh, in compression direction. So can you tell me which force is generally higher in terms of compressive or tensile strength? Any material in general. If I am applying means if I am applying compressive force, suppose 100 kilonewtons I am applying on one material. Okay, and if I'm applying same amount of the force 100 kilonewtons but in opposite direction, in both of the cases, uh, in which case material may tend to fail faster, in tensile mode or compressive mode? You are getting my question, right?
in tensile mode, sir?
Yeah, tensile mode it will fail much faster in orders of tens of degrees. Like suppose this material, some x material failing at 10 kilonewtons, in compressive load this may fail at 100 kilonewtons. That means 10 times of strength more in terms of compressive case compared to tensile case. It is case for all most of the materials exhibit similar properties. Compressive strength always higher than the almost 10 to 15 times higher than the tensile strength. Okay, coming to shear strength. What is the shear strength we can say? We see two strengths, right? One is the direction of the applying force, no? So what is the shear strength?
So, sir, in shear, we are applying force parallel to the surface.
Yes, that's good.
So
Same.
it gives resistance
Yeah,
while applying force parallel to the surface because it is basically the shear force that we are applying,
yeah.
as it is opposite to the tensile, which is a normal force.
Yes, yes, that's good. It is morely direction of the force we are applying. Once we this time we are applying the force in the direction of. You are able to see, right, whatever I'm drawing. You are
Yes,
seeing it.
yes, sir.
Yeah. Okay, okay, that's good then. Okay, we are applying the force in this direction. Okay. So how much it is not like a normal to the force. It is applying at a how much amount of the force required to move a certain unit length. It is all is the all properties. I mean, not all. Most of the properties we are comparing for changing the unit to uh, dimension of the material, how much amount of the force we have to apply. So we are comparing with which kind of force we are applying. In tensile, we are applying opposite way. In compressive, we are opposite way, but in compression mode. In shear, we are applying in shear mode. Okay. What is the impact strength? This one is also applying the force, but applying in which way we are applying. We see, right, three modes we are seeing. One is compress tensile means we are applying away from the body, this side and this side. Compressor means towards the body. Shear means along, I mean, a bit along the body. So in impact, how we are applying? Any idea? In name itself, it has answer. Impact strength.
Actually, in this we are hitting.
No, we are not eating. We are not eating impact.
Applied load.
Applied?
Suddenly applied load.
Yes, yes, that's good. So
Suddenly.
yeah, that's good, that's good. You're right. You're right, absolutely right. Okay. In in case of tensile or compressive, we are applying load very gradually. First we apply 10 kilonewtons, then I increase to 20, 30, like that. But in impact strength, when we measuring it, we applied a sudden load. It like a throwing a bullet at a fixed plate. Okay, it is a entire load applied at a sudden. So metal property is much more. Suppose if I have a material, if I am testing it compressive strength. Okay, I have a material, I am testing it compressive strength. Okay, but if in compressive strength, suppose it's showing like 100 kilonewtons, but if I am applying a 100 kilonewtons in terms of sudden impact load, it may not fail at 100 kilonewtons, but it may fail at 80 kilonewtons or 70 kilonewtons. So it is different from the way of applying the load also. So in impact load, it is so sorry. So it is mostly way we are applying. Here, tense in case of these three, we are direction of the load we are applying. In impact strength, we are seeing way. I mean, how much rapid we are applying the strength force. Okay, we are measuring the same thing. How much amount of the distance changing per unit to force we are applying, but way we are applying here. Okay, you got it right up to fourth point, fourth one. Oh, okay. Yeah, that's good. Okay. Next, coming to fatigue strength. How you can say like fatigue strength?
Sir,
Any?
actually, fatigue is a repeated load,
Yeah, yeah.
which
It
is
is
varying with
also
time.
yeah. It is also same thing, but we are applying the load continuously, repeatedly. At what frequency? At even though it is a less amount of the load, it will because of it is applying repeatedly for a unit of the time, it will break. So by that we can measure the what is the fatigue strength. Like if I want to break a iron wire, I can't break with my hand just normally. But if I am twisting it for 10 times or 20 times at a point, it will break. That is fatigue stress. I mean fatigue failure, right? That is the fatigue strength. Okay, what about creep? Creep?
Sir, a creep is a permanent deformation at elevated temperature at constant load.
Yeah, that's good. That's good. It is also constant load we are applying for more duration of time at elevated temperature. At when temperature increases, material strength will be reduces, right? But we are applying load at constant. It is like a I am holding the glass of water. It won't feel like much problem for me. But if I'm holding it for 10 hours, it is definitely have a lot of impact on my hand, right? It is a similar kind of concept in creep. We are applying the load for a duration of the time, how it is even the small load, how it is affecting the material. And we are also comparing with the temperature, because temperature is crucial factor in terms of determining the properties of the strength of a material, right? When the temperature increases, all the time the strength of the material reduces. Okay. Okay, what is the elasticity? We already discussed in elastomers and elasticity and plasticity. We already see here, right? This is a fundamental differentiation between these two kind of materials. What is the difference between elasticity and plasticity? These materials names also after that property only. No, not this one. I think that's wrong way of saying. But yeah, both to exhibit the
It is a property of a material
yeah yes
by virtue of which it regains its original shape after deformation in elastic. So that is elasticity,
uh,
elastic material.
sorry, come again, come again. Please can say once more, please.
Sir, actually, the elasticity is a property of a material by
Okay.
virtue of which it regains its original shape
Yeah, yeah,
and
that's good.
size
That's good.
after
And
deformation.
yeah,
But in
so
plasticity, it does not get its original shape
yeah,
after deformation.
yes, yes, that's correct. If some elasticity means if in the stress strain diagram, we can see if material, if I'm applying some force, if it is reached up to here, if I release that load, it will come back to its original position. So it has the elastic property. It is called the elastic property. In plastic property, plasticity means if I'm applying the force up to here, it will elongate, it won't break, but when I'm releasing the load, it won't reach to the original position, but it will dimensions will be changes, right? So this is called the plasticity. Okay, coming to resilience. What is the resilience? Any idea what is resilience?
Actually, it is related to energy. It is a amount of energy absorbed by the material till elastic region.
Okay, okay. And amount of the
It's
energy
actually
absorbed is
it
not the
is
one. Furthermore, continue bit more.
okay. Actually, it is a area under curved till elastic region.
No, no, no. That is toughness. That is a different one. You are saying about toughness. Amount of the energy absorbed. It is called the toughness. Resilience is different.
Sir, actually, the toughness is, I think, up to fracture, na?
Yeah, up to fracture. Okay, it is up to elastic region.
Elastic region.
Yes,
Yes, sir.
yes. That means how much amount of the energy it is absorbed and it releases back. Okay, that means it will regain its original position. I mean, yeah, you are saying whatever is the correct. Here is the area under this curve up to here only. Resilience. Okay. In terms of toughness, this line will reach up to here. How to at the fracture point? It is the toughness amount of the area under this curve. Don't worry about this diagram because I'm drawing it. Okay, leave it. So coming to ductility. So what is ductility? Ductility is somewhat has a relationship with the tensile strength. So what is ductility?
It is a
It
property.
is the property of material
Mm,
can be drawn into thin wire.
yeah, but property of drawn into thin wires. On which direction of the force we are applying? Here is the direction of the force is the crucial one. Okay.
So the direction of the force is same as the direction of elongation.
Yeah. Uh, no. It is actually so if I am applying force in this direction and this one also this direction, so it will elongate to this body will elongate in same direction only, right? Oh, no. You are saying I think bit differently. Okay. In opposite way, like tensile strength, what we are applying in opposite direction, the opposite, I mean, pulling action. In that way, how much amount of the material deformed it is called as a ductility. What about malleability?
Actually, it is in the form of thin sheets.
Yeah,
It is a
yeah.
property.
Then how we differentiate between ductility and malleability?
Okay.
Both
So
are.
in
Mm,
sir, in malleability, there is means there is a force which is acting, I think, in all the directions.
no, not that one.
Means,
So what is the difference? We can say both are exactly similar property, but we are see here all we discuss only about the type force applying, in which direction we are applying, how much amount of the change, right? In ductility also similar thing, malleability also similar thing. In both cases we are applying the force, but we are seeing in both cases we are seeing the amount of the change in material. But what is difference is that direction of the force we are applying. So in ductility, what we can say? Any idea? Ductility and malleability. Any guess? Okay. Yes. So in ductility, we can correlate with that tensile strength. How we are testing in this body, we are applying force opposite this way, right? Hmm? So when we applying this force, how much amount of the body changing will gives the ductility. You got it? This is everybody. I mean, we are aware of that, right? Ductility.
Yes.
So in malleability, same thing, but when we apply in the compressive strength here, not the tensile strength. Okay, compressive strength. How much amount of the material it is deforming? If I am applying compressive strength, it may also deform, right? It will height will be reduced, but width will height will reduce, but width will be increased. So here also it is elongating material, right? This is called malleability. It is only direction of the force we are applying, how it is changing. So we can correlate like ductility with the tensile strength, compressive strength correlation with the malleability. Okay, similar thing, both are similar, but direction of the force is the difference. Okay, coming to brittleness. What is the brittleness?
actually, the material fails suddenly after elastic region.
Yeah, that's good. It without a plastic deformation. Okay, there is no such thing like a plastic deformation will be there. Immediately it will break. The material will be break when we apply the force. Okay, that is called brittleness. Okay, toughness we already discussed it, right? Amount of the energy absorbed before it fails. It is much more. We can relate with toughness with resilience, but it is up to elastic limit. It is up to failure. I mean, including the plastic region also. Okay, coming to hardness. What is hardness? What is hardness? Any idea?
Sir, actually, it is a property of a material which resists indentation and penetration.
Yeah. it is how much it is resistance to make a indentation. Yeah, you are correct. It is how harder means it is much more difficult to make any scratches or any indentations on the surface. It is yeah. What about stiffness?
Is load per unit deflection.
Yeah, okay. Missionability, weldability, and abrasive resistance. These are all are the mechanical properties. Because why I'm focusing more on here is that every uh, we are I think most of the people from mechanical engineering and any thing we are design or any consideration, these properties are very crucial for the next consideration. Okay, missionability means how easily it can be uh, mission.
Machine.
Yeah, okay. Okay, if I have a material which has a higher hardness, less ductility, so can we call it as a good missionability? Higher hardness and higher brittleness, less ductility. Can I call it as a good missionable material?
It has
No.
low machinability.
Yes, yes. So we need which kind of properties we can call it as a missionable, good missionability?
It should be more ductile and less brittle
Yeah, yeah.
Less hardness.
Yeah,
and less.
we can't say like more ductile because if we have a very higher ductility, so chip will not break. Chip will be continuous chip, right? It is difficult to take from the material, na? So we want to brittleness also in some cases, but less hardness is the crucial one in missionability. Okay, less hardness and brittleness. Some cases, see, some chips are we see, right, machining, during machining some chips are very small chips, but some are very longer chips. So longer chips are also difficult to remove. That is also miscibility will reduce, right? So it is a somewhat balance. It is not like a too brittle means it may damage the our base, our machining workpiece also. So it is like a somewhat balance between the brittleness and hardness, ductility. Okay, so that comes the brittle machinability. Weldability. What is weldability?
Ability to get weld.
Yes, yes. So if I have a cast iron, if I have a mild steel, in both of the cases, which one has the good weldability in general,
For
general?
mild steel.
Yes, yes. It is mostly related to the chemical composition and microstructural perspective that will comes under these properties. Okay, this one is much more depending on much more gives the properties of physical properties, and these physical properties related will somewhat relate. I mean, gives the properties of mechanical properties. Dimensional properties is actually, it should be comes after this one. It is depending. I mean, it is the byproduct of these properties. If has the much more brittleness, we can say like when do we doing the machining, we can say like much more higher roughness it can produce, and it is comes under this way, right? Here it's supposed to be come here, but okay, leave it. Abrasive resistance, final one. What is abrasive resistance? Okay, what is abrasion?
So actually, it is a removal of material from the surface.
Yeah, removal of the material from surface. Okay, how it is different from machining? How it is different from the machining? Abrasion. How it is different from machining? General normal machining. I mean, like lathe machining or any other machining. How it is different from the abrasive machining? We all aware of abrasive machining, right? What in that case, what will happen? Abrasive means small particles. Okay, small harder particles. Okay, you can say sand. We have a sand. So if you see some JCB or something, that cup is the which take the material. So what kind of it will erode in terms of abrasion, right? Because of small particles continuously touches on it, right? So if you see water flowing a river or waterfall, okay, bottom rocks are smooth, very smooth. We can see the because of abrasive action, because the water continuously comes and hit the surface. Small particles will continuously hitting. In Lake Misna, that case, we have a single point of cutting tool, or I mean, one cutting tool will be there. It is a not a small particles, a solid piece which we'll use for the removal of material. But in abrasion, we are using very small finer particles, continuously applying on a workpiece to remove it. Abrasion resistance means resistance to removal of the material by this one. Okay, you are getting right? Yeah. Any doubts? Still, any
Sir,
queries from? Yeah,
yes, sir.
yeah.
Hardness and abrasion resistance, is there any similarity?
Yeah,
Can
yeah. Okay, okay, okay. I will explain that part now. Okay. So I have a surface. Okay, just assume this one is a some workpiece. I have it. So it has a very good hardness. Okay. So I am trying to remove the material by applying some amount of force here, like abrasive particles. And yeah, it is one somewhat if hardness is more, that means it will result in higher abrasive resistance. But not only that factor, right? Suppose the way of removal of the material also crucial, right? Suppose if I'm applying the direction of the force here, if I think I am, yeah, I think I will use this one. Yeah. So this is the mode of the failure, removal of the material, right? This part of the once it will impend, and this part of the material will remove. This is the abrasive machining or abrasive way of material removal. Hardness is uh, how much of the strength, I mean, how much of the, I mean, we can say like directly proportional to the abrasive resistance, but not totally. Okay. If I have a very smooth surface, not smooth, rubber. If I have a tie rubber, right? If I am applying how many amount of the particles, it will not remove the material. So it is abrasive strength is much higher. You are getting my point, right? Okay. It is a solid brittle surface. It has very high hardness. Okay. One workpiece is very solid surface at a very high hardness. I have another surface here which has very less hardness, but it is a rubber. Assume it is a rubber. Okay. So I am in both cases I am applying the sand particles to remove the material. Even though it has less hardness, I can confidently say like this material removal rate is much higher than the this material removal rate. You are getting my point?
yes, sir.
Yeah, because rubber can absorb that energy and not results in material removal. But here it will fail as a brittle failure because it want to absorb like a rubber, right? So it will
Yes,
fail brittle and it will remove. So even though it has higher hardness, it will fail faster than the this one. Some cases it will never, it will how much amount of the I'm pouring the sand, it will not break because it immediately that sand particle absorption, it will immediately take it. You got it?
yes, sir. Yes.
Yeah, that's it. Any other queries? For still now, because these properties are crucial because the main heading of the subject itself, nature and the properties of materials, right? So once we understand this part and remaining all whatever we discuss, it will be much more easier to go through.
Sir, I have one doubt.
Yeah, yes,
Sir, can we say if we have high ductility,
yes,
then we have high tensile strength? Means, can we say this statement?
No, ductility means ductility. Suppose if I have a workpiece here, this is my workpiece. If I'm applying the force in this direction, tensile force, okay, similar way. So it is applying the force, okay. I'm applying the 10 kilonewtons only. Okay, certain material I'm applying only 10 kilonewtons. But by 10 kilonewtons itself, it elongated up to here. Okay, so compared to initial length, it is increased by 1 centimeters. Okay, ductility we can say like 1 centimeter. After that, it will break. Okay, I have to another material, but it require 100 kilonewtons to get this 1 centimeter of change. Okay, in both cases ductility is same, uh, but at a 1 centimeter of length, in both cases both are break, but the amount of the force is different. In one case of 10 kilonewton is enough for the breaking of the material, but in another case it required 100 kilonewtons to break it, to reach the 1 centimeter of the length. So we can't, ductility is how much amount of the change in the length, but tensile strength is how much amount of the force required to change that length. You are getting the reference, right?
Sir, but if we have two material have same ductility, means I think the force required is same for both of the material, or not,
No,
sir?
no, no, no. No, both. It need not to be. How it can be if so. Okay. Um, assume like you have a aluminum rod and you have a steel rod. Both are same length. Okay. I give you both of them, and you have to elongate both two are lengths are 10 centimeters only. Okay. You have to make them 11 centimeters. Aluminum and iron. Okay, will you apply the same amount of the force for the elongation of 11 centimeters, both of them?
No, sir. Force will be different because these are two different material.
Yes,
Means they are
yes.
having different ductility as well.
No, ductility is amount of the change. Yeah, okay, different ductility means before failure, how much plastically deformed, right? Ductility
Yes,
means
sir.
what is ductility means? How much amount of the plastic deformation while applying the force opposite way, right?
Yes, sir.
Yeah, length, okay. But tensile strength is how much amount of the force. See here it is we are measuring the amount of the force, okay. In ductility we are measuring the amount of the change in dimension, length. What we apply, I mean, testing part both are similar, but what we measuring is the different. Okay, in ductility, suppose okay, in I will bit clarify that one. Okay, so I have a two iron rods. Okay, no, one iron rod and one aluminum rod. Okay,
Sir, actually, you differentiate these two terms
okay,
in terms of same material. Then it will
yeah,
be, I think,
okay,
more easy
yeah,
to understand. Means I am actually, sir, I am unable to understand. Like in some of the research paper, they are telling if we have more percentage elongation means more tensile strength. Means they have written one statement like
okay, okay, okay,
uh,
okay,
sir,
okay,
actually, sir, what is my doubt
mm,
is,
mm,
sir, actually, I am working in composite
okay, yes,
in my research.
okay,
So, sir, if we say the material, so
mm,
the property of the material is something different than alloys.
yeah, yeah,
Because in alloys we have the solute atoms and movement of the solute atoms and movement of the dislocation we are tracking, and then we are saying what will happen if we stretch the material.
yes, okay,
So, but in case of composite, it is something different from the alloys because we are
okay,
inserting some particle.
yeah, yeah,
We are reinforcing some particle. Means
okay,
in alloys we are reinforcing some particle in that, and then
okay,
we are deciding the property.
yes,
So, sir, if we say
mm,
if we are applying some nanoparticle
mm,
and we are making composite, then we are telling tensile strength is becoming more and more as
okay,
compared to alloy.
okay,
But this particle is brittle in nature.
okay, Okay.
So let us take example if we have aluminum alloy and
Okay.
if we are inserting some nanoparticle in that by using
Okay.
steel casting process or any
Okay.
process.
For
So
example,
after,
titanium oxide you are inserting into it.
yes, sir.
Yeah,
So
okay.
after inserting these particles, the hardness is getting increased as
Yes.
well as the tensile strength is also getting increased.
Yes. Okay.
Yes. So what is the reason of increment of tensile strength in terms of composite or hardness? Means
Okay. Yeah.
what
Yeah.
happens inside it
Yeah.
that it is increasing the tensile strength.
Okay. Okay. Let me explain that part. Okay. So how we measure the tensile strength we will see. Okay. Tensile strength we already see how in opposite direction we are applying. So some material have the elongation. Suppose this is the some aluminum alloy, some alloy I have it. Okay. So when I'm applying pressure, it is expanding. Okay, 10 centimeters to it is maximum. It is expand up to, for example, 13 centimeters. Okay, then it will break. Okay, I see the reading. How much amount of the force it required measure the tensile strength. Okay, uh, is around for example 100 kilonewtons. Okay, so this I can say like this material has the tensile strength of 100 kilonewtons, ductility of 30 percentage, because it is 10 centimeters to 13 centimeters it is expanded. Okay, I have a another aluminum composite. It is bit property is different. Okay, I took 10 centimeters of that composite and I am measuring it tensile strength. Okay, it elongated up to 12 centimeters only, but it observed the uh, 100 kilonewtons. Okay, in both cases I can say like both to have the equal tensile strength, but ductility is different. You are getting my point, right? In first case it expand up to 13 centimeters, but in this case it is only expand up to 12 centimeters, but both to required 100 kilonewtons to break it. You are getting my point, right? So I can say like second material, I think you are getting confused. I think I will draw one more here.
No, sir. I am understanding, sir. Yes.
Yeah, so in first case I can say more ductility, but both two cases I am seeing the same tensile strength, but one case has more ductility compared to other one. Okay, here hardness doesn't affect the tensile strength. Whatever the hardness, it is irrelevant, independent parameter here, hardness. Okay.
But sir, after reinforcement of some nanoparticle in
Okay.
alloys,
Okay.
so their tensile strength should decrease
Which
because
it's
their tensile strength should decrease, I think, after reinforcement of some particle because particle is brittle in nature.
yeah, but
So
no, actually it depends upon the matrix, right? How it is interacting with the material. I mean, material also important now. I mean, that is we can't say like it must to decrease the ductility, right? It could be. It is actually changing the microstructure, nanoparticle. In metal matrix, it is changing its microstructure totally. How it nucleates, how the grains forms, it is
sir,
changing, right?
actually, I am getting disturbed. I think some
Yeah,
mic is open.
yeah. Uh, hello, please, somebody who are that. Your name is please. Uh, hello, Kesav. Kesav. I think yeah. I'll.
Sorry, sir.
Yeah. Okay. Yeah. Now you can hear, right? Well,
Yes, sir.
yeah. Yeah. It is not a. We can't say like once we put nanoparticles into a composite, it must decrease the ductility or like that. It depends. It depends on the type of material and type of composition, right? It need not to be definitely reduce it, but it affects the how it is affecting it microstructure. That makes the crucial factor in determining its properties, right? Am I
So,
answering your question?
Sir, yes, sir, I have a last question.
Yeah.
Sir, actually, if we are refining the grain size,
Okay.
in a Hall pitch relation, if diameter is less, diameter of the grain is less, is its yield strength should be more, right?
Yeah.
So if we have fine grains,
Okay.
then we have more hardness, right?
Yeah. I mean,
Uh,
yeah, we can say yes. Okay.
Yeah, so if we have fine grain, more hardness,
Mm.
and also if we are applying load,
Mm.
then for the same elongation, it
Mm.
require more load. It require more load. Means if we have fine grain, then
Mm.
let's suppose we have two material, and in one material we have a grain size of 50 nanometer,
Mm.
and in another material the grain size is 100 nanometer.
Mm.
So I think in a 50 nanometer we have more hardness as well, and if we apply some load, then
Mm.
it for the same elongation it require more force in case of 50 nanometer material. 50 nanometer grain size material. Is it right, sir?
Mm, see, up to my knowledge, hardness is independent parameter
Sir,
to.
actually, why I am confused because
Mm.
in my research area,
Mm.
actually, I am reinforcing some nanoparticles in
Okay.
alloys, in
Okay.
aluminum alloys,
Okay.
and in some of the paper, what they are trying to conclude in their research is if we are increasing the volume fraction of the nanoparticle, the
Okay.
tensile strength as well as the hardness both are getting increased.
Okay.
So
Okay. Yeah.
the hardness is getting increased, which I understand because the
Okay.
hardness depends on the grain size or
Yes.
second
Yes.
phase precipitations.
Yes. Yes.
So if there is any second phase precipitates in
Mm.
between,
Mm.
so their hardness will increase anyhow.
Yes.
Or if we are able to refine the grain size, the hardness will increase. Yeah, that's right.
Yes.
But how they are telling their tensile strength is increasing means at what parameter they are measuring their tensile strength means they are telling if we are increasing the volume fraction of the nanoparticle, so
Mm.
till some level
Yeah.
the tensile strength the till some level tensile strength is following the curve of hardness
Yeah.
means
Okay. Okay.
the
Yeah.
hardness is increasing then tensile strength also increasing, but
Yes.
after certain volume fraction the tensile strength is getting reduced,
Okay. Okay.
but
Okay. Yeah.
hardness still remains increasing.
Okay. Okay. Let me come to one point here. So how we get the strength here? So we already see tensile strength, compressive strength, shear strength, impact strength. So how where we are getting this strength? Any idea? Where we are getting into the material? Some material has some strength. How it is getting it? Strength. How the what is the origin of the strength? Any idea? How the one material is getting strength?
I think there is a bond between their molecules
Yes, yes,
or atoms.
that is one factor. And second one is the resistance to dislocation motion. You know dislocations?
Yeah, yeah,
Yeah,
sir. Yeah,
yeah,
resistance to deflection motion.
yeah.
Yeah,
So if we add some reinforcement or nanoparticles or something into matrix, it will act as a barriers to move the dislocations, right?
right, sir.
So if dislocations are very tediously or very hard to move, that means it is a crack dislocations motion means which results in the crack propagation, right?
Yeah, yeah,
So
right,
if
sir.
dislocations motion is very difficult to move, so crack propagation also very difficult. Crack if crack is also very difficult to propagate, that means it is require more amount of the force to break it, right?
Okay,
So that means more amount of the energy required to break that one. That means tensile strength will increase. You are getting my point, right?
okay, okay, acha.
That
Okay,
from
okay.
there
You are
the
relating
strength
with the
is
crack.
coming. Okay.
Okay, okay. Means you are relating with the crack propagation inside the
Yes, yes.
material.
Yeah, any
But
material break by this one. Majorly, any material breaks by. See, if we have a finer grains to coarser grains, how the crack propagates. Okay, let me draw something here. Um, okay, this is the grains, right? Uh, so, any material will fail at the grain boundaries only here in
yes, sir.
so if nanoparticles are there here, suppose some nanoparticle is here, so if the crack is coming to here, break is happen, and when come to break here, it will stop this break and it will offers more amount of the force required to this one to break, right? So and once it cross, it will come here, so amount of the force required is becoming much higher in this case. So that makes the strength increasing. That's why uh, that is the major reason of any failure of the material, right? This crack propagation. If we stop the crack propagation, we can call it as a more strength. Suppose if I don't have a grains, if I have a pure crystal material, only single crystal material, there is no grains at all. Okay, in that case, how it will fail? Any idea? If it is a grain, I mean, in general, every iron, aluminum, everything has the grains. So failure will occur at grain propagation, right? Yeah. But in some cases, if there is no, I have a material which has the only one crystal structure, there is no grains at all. How it will break? Any idea? We already just I before I told na one reason of failure of the material. That is due to dislocations. Okay, crystal structure here, there is nothing to break. So see, any materials fail at the weakest point in this grain kind of structure. Weakest point is the grain boundary. Okay, if I have a single crystal, entire metal is single crystal, if I want to break it, it will only break by at the weakest point. Here is the weakest point is the dislocations of the crystal structure. You know, right? Dislocations motion. So once this
Sir,
yeah,
okay. So, sir, actually, dislocation is extra half plane, right?
yeah, extra
So,
plane, yes.
yeah. So, in if we have a perfect crystal, so there is no extra half plane because the all lattices are arranged properly in a single direction in an orderly way.
Yeah, but no crystal is purely perfect, right? There is always dislocations present in the system. Definitely, it will present. If not, it is very rare case. No, it is every material has a dislocations. That for sure. It is even the here grain boundary here failure occurring. It is not the entire between the grain. It is not breaking. It is a failure occurring at the always at the grain boundaries. This is the
But in a
weakest
single
point.
crystal, there is no grain boundary,
Yeah,
right,
so
sir?
that's
In a
why,
single crystal.
yeah, that's why it is fail at the dislocations motion, dislocations at the crystal structure. Uh, there is always present the some kind of there is no such thing like a perfect in the any crystal.
But sir, can
So
we say there is, can we say, is there any dislocation inside the grain?
um,
Inside
uh,
one grain. Let us suppose we have one grain. So
okay.
can we say that there is a dislocation present in it?
Yes, dislocations, yeah, it typically
Be-
presents. Every material, every crystal has some kind of dislocations, right? It's like a arrangement of the atoms, right? If you suppose you have a big box, you have a marbles in it. If you throw it, you can say like you can't say like everything arranged in a perfect order. There will be some disturbance at the some matrix point of, right? It is the nature of the anything. There will be dislocations of that. If in ideal case, if you assume there is no dislocations at all, everything is a pure crystal. Still, when you apply in the force, uh, there uh, there may generate the because of suppose if we applying the force and force, uh, because of that
Sir,
force, the crystal structure.
sir,
Yeah.
I think if we have a dislocation, then
Hmm.
we have some extra half plane means there is some distortion in lattice arrangement,
Yes.
right, sir?
Yes. Yes. Yes.
So if there is a perfect crystal
Hmm.
and if this made up of one single grain, so I think inside this grain
Hmm.
there should not be any dislocation because it is orderly arranged inside, na?
Yeah, let me come to that point. Okay, there is okay. So we see the first mode is at grain boundaries it is failing. If there is no grains at all, it is failing by dislocations. If there is no dislocations anything, if only pure crystal is there, how it will fail is that what is the next weakest point after the dislocations, in your opinion? Just rough idea. It is to learning point of view, right? What is the next weakest point in the any material after dislocations? If there is no dislocations, nothing is there, pure crystal. So where I can break it? Weakest point in a material. It's
I think
atomic
so. There
bond.
is no.
It's atomic bond, right? What is the crystal structure made up of? Pure crystal structure made up of atomic bonds, na?
Atomic bomb.
Yeah, that is the there is no imperfections, means that is the next to weakest point, right? Weakest point means uh, atomic between the two atomic bonds. This is the possible weakest point, right?
That means it does not remains the same grain. Means it becomes
Yeah,
different grains.
yeah. See here,
It becomes,
here strength required to break is very less. Relatively, it is less. Here you require very high strength. Here you require much more higher strength because you are breaking at the atomic bonds. These are the much more strong bonds. Okay, compared to that one, dislocations motion is bit easier. Here nothing is breaking, but you are moving on dislocation from one place to other place. It requires bit less energy compared to this one. Compared to that one, breaking at the grain boundaries is much more easier. Okay, relatively I am speaking. Now you got it.
yes, sir. Yes, sir. I am getting.
Yeah, that's the major difference how failure occurs. So coming to tensile strength is tensile compressors here and impact. All these failures are dealing with this kind of failure it is occurring. Okay,
Okay. But sir,
that's
brittle material has more tensile strength. What is your opinion in that?
brittle material has
Because
the
we have
more.
less elongation in brittle material.
No. Brittle material, brittleness is you can say like here brittleness, ductility.
Actually, why I'm asking, because if we are
Mhm.
reinforcing the nanoparticle,
Yes.
means the composite becomes brittle, because the reinforcement is only feasible, and only that we are studying reinforcement is because of we have a ductile matrix,
Mhm.
and if we are reinforcing brittle particle,
Mhm.
then we will have some individual property of ductility as well as the brittlity.
See, no, it need not to be. See, if you reinforce the nanoparticles, it need not to be entire material should be brittle, right? See, if the nanoparticle could come and sit here in the grains, okay? So when we expanding it, the ductility is this coarser grains could may elongate, and this particle only to stop the motion, right? It is need not to be. You are getting my point, right? It is need not to be entire metal should be brittle. We are putting a
Okay,
nanoparticles
so
of brittle one. It will increases its strength, but to entire metal composite metal matrix still in be ductile form also.
okay, so sir, you are considering strength means what you are considering? You are considering the hardness of it also.
No,
Means,
hardness is resistance to scratch. How much it is hard to make a indentation and how much it is hard to make a scratch or something like that.
okay,
Okay.
so if we are inserting the nanoparticle, it is just sitting on at the grain boundaries.
Mhm.
So if we are stretching it, so
Mhm.
it is very hard to stretch, right?
Yeah, it will hard to stretch means it has more strength. It is in other words we can say like it is increasing its strength. Okay.
Okay, so
Yeah,
after reinforcement, the tensile strength will increase anyhow.
yeah, definitely means mostly it is depending on the composition, right? Composition is very crucial, right? If now how it is interacting with the metal matrix, how it is better compactability also important, na?
Okay, means it may reduce also. Tensile
Yeah,
strength may
yeah,
reduce
depends
also.
on the properties of the material, right? So we always take the properties reinforcements which shows the increasing in strength, right? So that is what is our objective, na? So increase the strength finally. So
Yes, sir.
which nanoparticles increases its strength, that is we will take.
Okay. So, sir, in strength only we are considering tensile strength, right?
Yeah, we can test compressive strength. Why not? We just to have to change the direction of the force. Okay.
Okay, sir.
Yeah.
Okay, okay.
Yeah. Any queries, others? So otherwise we can go to problem solving because yeah, the assignment solving and like that. Any queries? Because this is a for any mechanical or anything, this is the fundamentals for understanding the stuff, right? Yeah. Okay, shall I go forward? Okay. Okay, coming to assignment solving. Oh, sorry. Okay. So, what could be the answer? First one. What is the main advantage of using honeycomb structure in engineering applications? What we can say? What is the high strength to weight ratio, or low cost of production, easy of manufacturability, or good electrical conductivity? You know, right? What is honeycomb structure in engineering applications?
So I think it is high strength to weight ratio.
High strength to weight ratio. Yeah, that's good. Because low cost of productivity is not one because it is compared to bulk product, it is making is much more costlier process. Ease of manufacturing definitely it is not good electrical conductivity. Honeycomb structures do not have that much good electrical conductivity because of it is not conducting. So okay, leave it. So coming to next one, what is the primary difference between metals and non-metals based on their atomic structure? We already seen here so yeah, what kind of structures we are going to see in metals and what kind of atomic structure we see in ceramics or other one? We already discussed it, right? What it is? What kind of atomic structure we can see in metals? There are three atomic structures are there, right? Ionic bonding.
So in metal we have ionic bond, and in ceramics we have ionic as well as covalent bond.
Yeah, that's good. But metallic, we have ionic bond. No, not that one. Metallic bond, right? There are three bonds, na? Ionic, covalent, and metallic bonds. Metals are mostly composed of metallic bonds only, na? So that's why, right? Free electrons are much more available in the matrix, so it will have good electrical conductivity, na? That's why metallic ceramics have higher strength, I mean less higher brittleness and higher strength also because for changing a unit dimension you require more amount of force. So here you have the ionic bond and covalent bond. Those bonds are very strong. So that's why we get the more strength. So coming to next question. Yeah, what is the primary difference between metal and non-metallic one? First option is metals have the loosely held outer electrons, while non-metallics has the tightly held outer electrons. Or in second option, we have metals have the held outer electrons, non-metals have the loosely held outer electrons. In both our atomic structures have same atomic structure. In non-metallics are isotopic. So what could be the answer? Any idea? So we can approach it in a different way. So metals generally have the higher electrical conductivity, right? So higher electrical conductivity means electrons should able to easily pass through it. Okay, if electrons should be easily passed through a material, that means outer electrons should be uh, loosely hold or tightly hold, or say both cases it will be same.
Option A. Option
Option
A is correct.
Yeah, option A is correct because in metallic case electrons are loosely because it is a valence electrons are very less valence electrons, so it will be loosely hold. In non-metallics means there are covalent bond in ionic bond. Both two are very much strongly hold the electrons, right? So it is hard to move them. So first option is the right one. Okay, coming to this one, which one you are seeing? Which one could be the right one? There are only two independent elastic constants. You know what is elastic constant? Anyone?
Yes, sir. Like E, G, and U.
Yeah, yes. What is E?
Young's modulus of elasticity.
Yes. G means?
G is modulus of rigidity.
Yes. Okay, modulus of elasticity, how we will measure it?
Modulus of elasticity is equal to stress by strain.
Yeah, that's good. And rigidity? What?
Rigidity is tau by 5.
Yeah, okay. So there are only two independent elastic. Okay, see, first we have to see this statement. Okay, which of the above statement are true for the linearly elastic? Okay, that means stress and strain are linear, not okay. Next, homogeneous. Homogeneous means what is different between homogeneous and isotropic?
Sir, actually, in homogeneous means there is a same property in, I
Uh,
think, in a same direction we have the same property. But in isotropy, if we
mm,
take any point and move in any direction,
uh,
property is same.
yeah, yeah. Homogeneous means entire matrix is wherever you see it will be same. Isotropic means whichever direction you are applying, seeing the properties, with direction it won't change any change. You are correct.
Actually, isotropic property depends on the point.
Y-
Like if we take any point, move in any direction, it will be same.
Yeah, yeah. That's the one. See,
But point to
mm,
point, it may vary. But
yeah.
at any particular point in any direction, it will be same.
See, wow, what? Sorry, I didn't get you properly. Please, can you explain?
Sir, actually, what I am trying to say is, if we take material is isotropic means
Mm,
if we take any point in a material
mm,
and we move in any direction, either
mm.
x, y, and
Yeah,
z,
yeah, yeah.
the property remains same.
Yeah, yeah.
Like
That's
if
good.
stress is sigma, sigma, sigma in x,
Yeah,
y, and z direction.
yeah.
But homogeneous means if we have the stress like in x direction is sigma 1,
Mm,
so the y direction it will be sigma 2 and z direction it will be sigma 3. But
okay,
if we take one
okay,
single direction in
okay.
x, it will be same.
Yeah, okay,
In
okay.
single direction, it will be same.
Mm, okay. Okay, in same thing, you are correct, but can I put it in another word? Okay, I mean, in we are not going into that much, I mean, depth way. Ordinary way, if we see isotropic, we can assume like if you have a wires, bunch of wires, if I pulling in a longitudinal direction, we can say like more strength. But if you apply in lateral direction, it will easily break. Like that. I mean, yeah, I'm not saying you are absolutely correct, but I'm saying like in another way. I'm saying same word. I'm saying in another way. Homogeneous means wherever we see the properties like homogeneously mixed, like composition wise, if we see material at one point how much composition is there, similar way it is similar in all location of the material. Okay, so in this case, in this kind of material, which kind of statements are correct? Okay, first one is there are only two independent elastic constants. Second one is elastic constants are different in orthogonal direction. The orthogonal means opposite direction, right? 90 degrees. Okay, and material properties are same everywhere, and elastic constants are same in all loaded directions, and material's ability to withstand shock loading. So which one could be correct? We have to consider these three conditions, right? Okay, we will break down one by one. Okay, so coming to this one, third one. Okay, we will material properties are same in everywhere, which
So
is
it should
nothing
be
but
option C.
yeah, option C. Okay, why? Oh, okay, option C. One option according to option C, first one is there are only two independent elastic constants. That's good. Elastic modulus and modulus of rigidity. And third one, metal properties are same at everywhere. It is nothing but homogeneous. Okay. And next one is fourth. Fourth is elastic constant same in all directions. That means isotropic materials. It means it is only so. Yes, 3, 1, correct. Okay, next coming to 2, elastic constant are different in orthogonal direction. It is wrong because it is he specifically mentioned isotropic means it should be same. So that means 2 is wrong. What about fifth one? Why you think like not A but C only? Why not fifth is we can't consider? Why not we can consider A? A is the answer. Why not? Why you are removing the fifth option? material has the ability to
Think,
withstand.
yeah, shock loading. I
Yeah,
think it should be true
yeah, because it is
because it is ideal material.
general word. It is, we can say, like a general word. Every material has some amount of the soft load absorption, right? It is not like a he didn't mention like a certain amount, but he said like it can it has the ability to withstand the shock load. So yeah, it is true. So we can say A is the answer. Okay, because it is a bit fifth point is a bit general load. It can be applicable to most of any kind of materials, right? Every material generally have some amount of shock load absorption, right? So yeah, yeah. Coming to this one, so how you are going to solve it? So what is the Poisson's ratio? Anyone have any idea?
It is lateral strain by longitudinal strain
Yes,
with
yes.
minus 1.
Yeah, that's good. So how it is related to Young's modulus and modulus of rigidity?
I think E is equal to 2G into 1 plus mu. I think I don't remember
Yeah,
it.
yeah, yeah, yeah. This is the formula. So we just have to place the E equal times modulus. G is the modulus of rigidity. We just have to place them. So we get the Poisson's ratio. So can you guess any what could be the answer? So you can take E as a 2.5, G as a 1. So now you can calculate. Here is a 2.5. Here is the 1. What could be the mu? Try to solve this one. Here you can E as a 2.5, G as a 1. So G into 1 means 2 into 1, 2. 2 into 2 plus 2 mu equal to 2.5. Okay. The 2 goes that way. That means 2.5 minus 2. What it will be? And this 2 will be go there. Then what could be the answer? Oh, what happened? What happened? What happened? Hmm? Net problem? Net problem. నాకు ఈ టైంలో ఇబ్బంది పెడుతుంది. ఇంకొక 20 నిమిషాలు ఉంది. కింద మొబైల్ డేటాతో చేస్తాను మరి. చూద్దాం. చివరికి వచ్చి ఇబ్బంది పెట్టండి. వైఫై ఆఫ్ చేసి ఆన్ చేసి ట్రై చూడు. కనెక్ట్ అవుతుంది. కనెక్ట్ అవ్వలేదంటే అప్పుడు చూద్దాం. కనెక్ట్ అయింది. మొత్తం అంతా పోయిందే. అందరు కట్ అయిపోయింది. కట్ అయిపోయినట్టుంది. Oh, okay. Sorry for the disturbance. Net connection was failed. Yeah, we yeah. You can see the screen right now. Yeah, you can see now. Hello, can you hear me? Hello. Okay.
Yes, sir.
Yeah. Yeah. Okay. Yeah. So this one we can just replace the these parameters elastic module and modulus of rigidity. So we can solve it by 0.25. Okay. Okay. Coming to next one. What is the primary mechanism responsible for the deformation in crystal material under stress? So we discussed before, right? So first one is breaking of the atomic bonds. Second one is movement of the dislocations with crystal structure. And third one is melting of the material. D is the none of the above. What could be the answer? We just previously discussed here. He mentioned like a pure crystal. In pure crystal, what could be the answer? Where is the weakest bond will be there in pure crystal? Any idea? Breaking of the atomic bonds is not the one, and movement of the dislocations in the crystal, or melting of the material, or none of the above. None of the above, not no, because melting of the material is a not the considered one. So in both of this one, which one is the weakest bond? We just discussed now previously. Here, this is the failure at the grains. This is the weakest bond, but it is happens at the uh, multigranular structure. But in a perfect crystal, there will be no grains, right? So next weakest bond will be dislocations, not the atomic bond. Atomic bond is the final strongest bond. Okay, so that means it will be dislocations. Dislocations is the crystal structure. Okay, coming to next question. Which one is the following is not correct for the aerogels? Okay, what is the aerogel? Anyone have any idea? What is the aerogel? Aerogel is what? Any guess? Final 15 minutes. 15 minutes. After that, we will conclude it. I mean, we will end this session for today. Let's say. Okay. Aerogel is the nothing but where is it? Yeah. Aerogel is nothing but structure. Gel means it is having a filling material inside a random structure matrix, right? Here, aero means only just normal air. Okay, gel means gel formed with air. So that means it is 95% is porous. So that means it is totally empty. So first one is correct. High conductivity, close to the copper. We don't know about it. Let's leave it for some time. High insulation capacity. So we can bit to both two are contradictory one, right? Because conductivity here insulation. Because can we say it is conductivity? No, because copper here aerosol means lot of disconnectivity is there from one to other. No? Just wait. Okay. So um, so it is very poor conductor. So we can say, but it is good insulator, very good insulator, and ultralight material. Yeah, because it is 95% pure means it is ultralight material. So which is not correct is the copper. It is not conductivity as the copper. Okay. Next, coming to next question. Which statement is the false for the oxalatic base cellular structure? What could be the answer? A. High negative Poisson ratio. What is the oxatic material? First, oxatic materials means which has a negative Poisson ratio. So negative Poisson ratio means once we applying the angular direction, here we can see once we applying direction opposite way, this in normal materials when we apply the force in opposite direction, this width will be radiuses, right? Width will be radiuses. But in oxatic materials, when we apply this force, the width will be increases. This is called oxatic material, right? Okay. Coming to where is the question? Yeah. Yeah. First one is negative Poisson's ratio. Yeah, it has negative Poisson's ratio. It is name itself saying like it should be have the negative Poisson's ratio. So second one is exotic cells have the re-entric angles. What is re-entric angle means? So okay, if I have a hexagonic structure, honeycomb structure. If I draw a line here, I think it should be in red color. Okay. So this angle is here, angle between this line and this one always makes the positive angle, right? But here re-entric angles means it should be the negative angle. So in oxatic materials, what happen, how the structure will be like? This will much more have the this kind of cellular structures. Okay. Here this portion is actually will be white color only. Yeah, this kind of structure. So in this case, which kind of angle we can see here? If we draw a line here, so here we can see positive angle, but here we can see negative angle. This angle we call it as a re-entry angles. Okay, and nature of the surface would be cyclone cyclistic surface. This is nothing but a dome kind of structures. A dome kind of structure. I mean, so if we bend here this kind of material, it will form a dome kind of structure. Okay, and nature of tendency of forming saddle type structure means you know horse saddle, it will be like a concave. It is contradictory to this one. So it will always form the dome kind of structure, but this is the not the one. So this is the wrong one. Okay. Okay. Coming to what is the hardness. So anyone can say what is the hardness? We already discussed now. What is the hardness? First one, resistance to plastic deformation or resistance to elastic deformation. or energy absorbed on deformation or energy released after deformation? Which one? Definitely not. Okay, we will come with eliminating one by one. Okay, energy released after deformation. It is not the one. Energy absorbed after deformation. Definitely, there is no energy absorption and release will be there, right? So it is heating up or heating, cooling down. It is not the case. So coming to these two, resistance to elastic deformation. We can't say like this is the one also not. Why not? Because elastic deformation in if we apply any hardness test, suppose if we take a hardness test here, yeah, here it would be better. So when we applying the force, it will come down. First indented will make a some hole. Then it will once we release the force, it will come back to some amount of the shape will be regained. Okay, first it will be a bigger hole, then it will bigger indentation, then it will form a smaller indentation. So we are not measuring the elastic deformation, we are measuring the final dimensions, that is the plastic deformation of the material. So it will be a resistance to plastic deformation. Okay. Okay, coming to next one. Yeah. So it is also similar to a problem which we see before. Can anyone solve? What is the answer? It is also same similar formula. Take a 2-3 minutes and try to solve. Okay, it is also similar formula which we are using, E equal to 2g into 1 plus mu. So here is E is the elastic modulus and G is the modulus of the rigidity, mu is the Poisson's ratio. Once we apply all of the E and mu, then we can solve this one. We can easily get the modulus of the rigidity. That will be, this one is the answer. Okay, coming to final question. What is the following is the not characteristics of the well-designed honeycomb structure? Okay, what could be the answer? Yes. Oh. First one is uniform cell size and shape. Can we say it is? Yeah, it is correct. Okay, because honeycomb structure always all unit cells are almost similar in size. Okay. Second one is high stiffness and strength. Yeah, definitely honeycomb structures are generally have high stiffness and high strength. Okay, and large amount of the filler material. This could be, may not be. And coming to fourth one, good resistance to buckling and crushing. Yeah, that is also a good part of the honeycomb structure. You know, right? Honeycomb structure, what is it? It is nothing but a this kind of structure, repeating the order. Like this, a repeating order will be there. Here is the white portion is the which we are filling. So here is he mentioned like large amount of the filling material. So here we usually take the as low as the material filling material we are taking. This hexagon shape is entirely is empty portion, right? So uh, this one is the among all this C is the could be the wrong answer. Large amount of filler layer is the not the one. It has a uniform cell size and shape. It has a higher stiffness and strength and good resistance to buckling and crushing. Okay. Okay. Any queries for today's session? I think that's all from today. Any queries, anything if you want to discuss, we can discuss, or if not, then we can conclude. Okay, let's see fast, quick recap of what we have seen today. Okay, so we see the type of materials. One is metallics and ceramics, glasses, elastomers, and polymers. Metallic means it has the atomic bond of metallic bond. Ceramics, it has the ionic and covalent bonds. Glasses has the amorphous structures. Elastomers means it has the higher elastic properties, and polymers means the it has a much more like plastic deformation. Okay, and coming to we see the type of material properties like chemical properties like composition, microstructure, crystal structure, and corrosion resistance. Dimensional properties, roughness, waviness, play, and physical properties like melting point, density, specific gravity, reflectivity, thermal conductivity, and thermal expansion like that. And mechanical properties, we all see them in depth, like tensile strength, compressive strength, shear strength, impact strength, fatigue strength, creep, elasticity, like that, and hardness, and so on. So, coming to we solve the different questions, and yeah, that's all for today. Thank you for joining. Any queries? If not, I think we can conclude for today now. If you want to. Okay, that's all for today. Thank you. Thank you. Bye bye. See you next Monday. Thank you.